Hey, have you heard the joke about gravity? I'm not going to tell it. It's too much of a downer. I'm kidding. Welcome to 8.3 of compound interest and our lesson. So let's get started. Whoop. So, as I mentioned, 8.3 is about compound interest, which helps. I'm just going to make it so that you guys can look at my face the whole time. Which helps explain why or what a lot of times is used for exponential growth and decay functions. Hopefully, it's exponential growth if we're talking about your money. So here it is, compound interest. So this is a very real scenario that you all will, most of you will probably have to do at some point. Cecil borrowed money to pay for his college education. So the bank allows Cecil to make no payments for the first 6 months after he graduates, but still charges interest. Cecil starts paying off his student loan 6 months after graduating. So you're going to be faced with a very similar situation. So if you get student loans, which a lot of people have to do student loans, you're going to have to pay them off. And a lot of these deferred payments after you graduate allows you a chance to get a job and kind of get financially secure, and it sounds all wonderful and great, and sometimes it's what you need. But it is good to understand the fine print. So what is a mathematical question we can ask? What's his interest rate? How is it being compounded? And how much money does he owe? And all those kinds of things. So we scroll down. Blah, blah, blah. 6 months after graduation, but still charges him interest of 0.5% per month. So let's answer the question. How much interest will the bank charge for the first 6 months after Cecil graduates, and that will eventually end up being an exponential function. Yay. So to answer this question, we're not going to go through all the strategy you need to answer this question, because let's just get straight into compound interest and how you can make it work for you. Those of you in personal finance, this might be a review, but hopefully maybe we can jump a little bit more deeper into the math behind some of the concepts you talk about in personal finance. So compound interest, so we're going to compare simple and compound interest. So if you don't know, there is simple interest and there is compound interest. So the question is, which one is better? Which one do you want? Which one do you want to avoid? Things like that. So the bank may pay simple interest, where a certain percent of just the principal is paid at regular intervals. So the principal is, let's say if you make an investment, is the amount of money that you initially put in, or if you're getting a loan, it is the initial amount of the loan. More commonly, banks pay compound interest, which is interest paid on both the principal and the accumulated interest. So Farah wants to deposit $500 she earned from her summer job into a savings account. Her local bank offers two types of savings accounts shown below. Your first one is your basic savings, no minimum balance, 3% annual simple interest. Or you have your reward saving, $500 minimum balance, 3% annual interest compounded yearly. So which one's better? So when you compare the two, you start off at 0 years, you have 500 in each one, but then after 5 years, your basic savings will go up $15 every single time. You'll have 575, whereas your compounded interest will go up each time it gets a little bit bigger. So basically, the more money you have in the bank, the more money you can then make off of it. And that is more so true with things like investments. That's also how rich people make money through investments. We'll talk about that more later. But anyway, so for each type of saving account, how is the balance after T years obtained from the balance after T minus 1 years for T greater than or equal to 1? AKA, when you go from year to year, what is the difference? So basic savings, from 1 year to the next, you add $15. The reward savings, you multiply by 1.03. So here, whenever you multiply, every time you have a bigger amount, you multiply by that same number, it's a bigger amount, you then get a bigger amount. So there's a slight difference here. You have more money in the rewards one here. And here it's just small, but when you start talking about like big numbers, you know, if you had like $1 million to invest or something like that, then all of a sudden the interest starts to add up. Not that I have $1 million sitting in my pocket, but whatever. For each type of savings account, what is an equation that gives the amount A of a money in an account as a function of time, T in years? So this is probably the more important part, is figuring out the equation so that we can then make predictions. So your simple account is a linear equation. So T is number of years. That's how many $15 you end up getting. Whereas your reward saving is an exponential function. And as you remember, I hope, an exponential function starts to look like this after a while. And if that represents your money, this is the function that I want, as opposed to this. Although I'm a big fan of my money going up either way. So how much money would Farah have in each type of saving after 10 years? So basic savings, you're just going to plug 10 into that T. So for your basic, your A is going to be equal to 500 plus 15 times 10. So that's 150, which is going to eventually equal 650. So then this other one, I'm going to have to actually probably use a calculator for. So 500, 1.03 to the power of 10. And I'm going to bust out the calculator for that one. Let's get out of there. Let's move my face so you can see stuff. Okay, so 500 times 1.03 to the power of 10 equals 671.96. So 671.96. So you're still not talking about a huge amount of money, but you're starting to see, I hope, that the compounded interest is giving you more money. And that's the point that they're trying to make, slash the mathematical equation of it. So which type of savings account should Farah get? And I hate this question. They're begging you to answer it this way. But the reality is these decisions are always going to be based on more than just how can I get the most money after 5 years. You know, what if Farah needs money next year, but she only invested, or she only did $500, but now she has to go below that minimum. Because you remember, there is a $500 minimum balance. So yes, it's worth noting that you can make more money off of this one, but your life dictates, the situation dictates which one is better for you and your goals. So is your goal to set the money in there and let it sit for a long time? Or is your money Or is your goal to have a bank account that you can then use like a rainy day fund? So whatever. It's not a good math lesson without some formulas, right? So here is one of our formulas. So model interest compounded yearly. They'll give us a more detailed formula later. But if an initial principal P is deposited into an account that pays interest compounded yearly, then the amount A of money in the account after T years is given by this equation right here, where R is the annual interest rate expressed as a decimal. So this bike costs $850 and is expected to depreciate 20% per year. So I love that. They gave us interest compounded yearly, and they gave us a depreciation situation. But this equation should work for both situations, whether you are gaining money or losing money. So we're going to start by, looks like, gaining money. Juan has $400 in savings account that pays 3.5 interest compounded yearly. He wants to use the money to buy a used mountain bike in 3 years. The current price of the new model that Juan wants is shown. That's where that comes from. As is the expected rate at which the bike depreciates or loses value. Will Juan have enough money to buy a used model of this bike in 3 years? I mean, is he not going to make any more money? But anyway, they're talking about just this $400. Will this $400 be able to buy this $850 bike in 3 years? Whatever number they gave us. So first, how much is this going to be in 3 years? So we have our principal, which is the 400. So remember, the principal is the initial amount of money that you invest or borrow or whatever. Then we have our interest rate that pays 3.5% as a decimal. So our R, our rate, is going to be 0.035. And then our T is 3 years. So then you plug all of that into this equation. You get this guy right here. And then you do some math. I would just shove all that in my calculator. And you get this amount of money at that point. So he's making a little bit of money, but not a huge amount. So let's see what happens to the bike's value. Why do you substitute that instead of that for R? Because percentages needs to be expressed as a decimal. Also, 3.5 will make this dramatically larger than 1, and all of a sudden you're going to have this huge curve. And that's not the reality of the situation. Okay, so that's what we got. Estimate the cost of the bike that Juan wants after 3 years. So we're going to use the same equation, except we're going to use the decay function. So if you remember, up here it said A is equal to the principal times 1 plus the rate T. So that's for growth. But depreciation, the cost is going down. And so it's kind of the same, except instead of 1 plus 0.20, it's 1 minus 0.20, which makes sense because since we know that it's going down, it depreciates by 20%, which is what it said up here. So we can kind of think of that as a negative 20%. So the price changes by a negative 20%. So math. Let's do some math. So we plug everything in. right there. So again, 1 plus a negative 0.2. So we're going to have 0.8 left over. That's where this 0.8 comes from. And then we do the math. The bike is going to cost $435 after 3 years. So that means that Juan will have enough and a tiny bit left over. He'll be able to go get some food, maybe, at the dollar store. I don't know. Why is the base of this exponential function less than 1? Because at this point we are in an exponential decay function because the price is going down, not going up. He will have enough money to buy the bike. Yay! Now, compound interest can be compounded either once a year or more than once a year. So again, this is another one of those things where if you're doing finance stuff, you might want to look into the fine print. So what happens if your interest is compounded more than once a year? So we were talking originally, this was our equation right here, but that's for it being compounded yearly. So what happens if it's compounded more than once a year? So basically, interest may be earned more often than once a year if interest is compounded n times per year, then the interest rate per compounding period is r over n. So here we go. This is the official formula for compound interest, where n is how many times it is compounded per year. So notice you have an n there and an n there. So it kind of makes sense. If it's yearly, then your n would just be 1. So that's why this turns into just r, and then 1 times t is still t. So this is something that you can remember rather than memorizing 2 separate formulas. So let's try it out. So Lisa deposits $1,500 into an account that pays 4.8 annual interest compounded monthly. What is the account balance after 3 years? How much time does it take the balance to reach $2,000? So based on our question, we can say that our principal is $1,500. Our rate in decimal form is 0.048. And since it's compounded monthly, our n is going to be 12, because there's 12 months in a year. And then our t is going to be, for the first half of that question, is going to be 3. So it's asking, what is the account balance after 3 years? So that's what we got out of the question. So then you just plug it into your formula and poof out an answer. So here's our initial formula. Here we plugged everything in. Notice there's 3 years, 0.48, all that good stuff. So then they just simplified it in steps. At this point, either here or here, you can plug it into a calculator and get our answer. So after 3 years, she's going to have approximately $1,731.83. We say approximately because I'm sure that this is a decimal point that went on and on and on, but we rounded to the nearest cent. Because who cares if you have 1/10 of the penny? So why n in this situation? So there's 12 months in a year, we talked about. And then the next one, to find the time it takes for the balance to reach 2,000, so our t is no longer 3, our t is now a variable. And the whole function would equal 2,000. So let's see here. So you can do this one of two ways. My brain always initially goes to y equals 2,000, so I would just set it equal to each other. But they're showing us a different way to do it on the calculator, and that is you graph y equals 2,000 along with our formula with everything plugged into it. So let's write that on the screen. So it's going to be 1,500 1 plus 0.048 over 12. And then 12, I'm writing x because that's what I'm going to have to plug into the calculator. So let's pull our calculator up, move my face, and so here we're going to go back to our graphing section. So again, that's this y equals button. So we're going to type in 1,500 parenthesis 1 plus, I'm going to use my parentheses again, 0.048 divided by 12. So the reason I don't do that first and then round is because you're introducing an additional rounding error. So that's why I just like to put the whole thing into my calculator. But you have to be careful with your parentheses. So I need another set. So this whole thing right here is being raised to the 12x. So my window is really weird right now. So so we need that, and we're looking for when does it hit 2,000. So we're going to make a line at y equals 2,000. So then let's look at our window. So our x minimum, 0, sure. Y minimum, we could probably put that at 0. Our y maximum, so we're only going up to, what, 2,000? So let's say 5,000. And I can't imagine it takes more than 10 years. So we'll see what happens with that. Bam! Got it right there. So just so that you can see what it looks like when you zoom out. So you have your exponential growth function, and then you have your straight line. So we're going to zoom back in. So that's why it's kind of important to know what your graph is supposed to look like, because this is all I need. So I see that they cross. We're going to go up to calculate, use the intersect button. Boop. First curve is our blue curve. Second curve is our red curve. And then it's going to make a guess. So the reason it says guess is if you have multiple graphs on there, or the same graph with multiple intersection points, then that's when you're going to have a little bit of weirdness. So when y equals 2,000, x is equal to 6.005. So I'm assuming that's going to be 6 years. Go away. So we find where the graphs intersect. So we did that. Now we have to use there. The blue graph represents the exponential function. The red graph represents a linear function. And the account balance reaches $2,000 after about 6 years, which is what we got. So this is, again, really important when you're starting to talk like financial planning. You know, how long until I can afford that car, that house, the new iPhone, the new whatever, iPad, I don't know. But you can use this to, you know, help you financially plan of how much money you're going to have in the future. So not that any of you are thinking about retirement yet, but this kind of stuff, super big in retirement. because you want to retire with plenty of money so you can live comfortably. All she wrote on compound interest. So long story short, take your information, plug it in the compound interest formula, and then poof, you get a number. So exponential growth is your compound interest. That's when you're making money. Depreciation is exponential decay. That's when something is losing value. So hopefully this was beneficial to you. Again, you're going to see all this stuff over and over and over again in your life. So it's good to kind of have a little bit of understanding. On that note, bye. See you in class. Make money.